Okay, so today we're covering Chapter 8, and this is covering hypothesis tests. Okay, and specifically hypothesis tests for categorical variables. Okay, but as far as hypothesis tests go, this is another tool or another method of statistical inference, okay? Let's say what was the other statistical inference method that we have learned? What's that? The other method for statistical inference that we've learned so far are the confidence intervals. Okay, and so when we're talking about statistical inference, it's where we are looking at a sample, and based on the sample, we're making a conclusion about the population. So with confidence intervals, you look at a sample, and you are making a statement or conclusion about the population. Okay, so you looked at a sample, based on what you see in the sample, you make a statement about the population proportion. Here, something similar. You look at a sample, and we're going to make a conclusion about the population. Okay. Okay, now I'll also write the other. Okay, and the key difference here is that with hypothesis testing, we start off with a belief, okay? And we call this initial belief the null hypothesis, okay? And that's why they're called hypothesis tests, okay? So I'll say with hypothesis testing, okay, we begin with an initial belief, or at least a testable claim, okay? Okay, and this is called the null hypothesis. So we're going to, we start with an initial belief. This is called the null hypothesis. And we say, well, let's assume this hypothesis or this belief is true. Okay? And then we say, well, if this were true, what would we expect the world to look like? Okay? ask, if it were true, what would the world look like? Or what would we expect So we have this idea of what to expect. We say, if this thing were true, what can we expect? And then we compare that expectation, or that idea of what to expect, with the reality. Okay? Okay? So what would the world look like? That's our expectation. And then we compare that with the reality, or the actual data that we see. Okay? If our expectation and the reality match pretty closely, then we have no reason to doubt our initial beliefs. Okay? It doesn't prove that the initial beliefs are true, but we have no reason to doubt them. Okay? On the other hand, if the expectation and the reality are very different from each other, okay, we have to side with reality, and we say, okay, well, because there's such a huge disparity between the reality and the expectation, then my beliefs that produce this expectation must be wrong. Okay, and that's basically what hypothesis testing is. So we compare the expectation to the reality. Okay, if expectation and reality are similar, okay, no reason to doubt our initial beliefs. Okay. If the expectation and reality are very different, okay, we side with reality. And conclude that our beliefs that produced our expectation are wrong. Okay, and so this is kind of the system of logic that we are going to employ in doing hypothesis testing. Okay. And the way we're going to say, and so there's kind of this question of, well, how do we know when the expectation and reality are similar and when the expectation and reality are very different, right? That seems like, well, that's how do we know when things are similar, right? Because if they're not exactly the same, like you're expecting something to look a certain way, and it's not exactly that way, but it's kind of similar, but, well, you know, or there's some differences, then you have to wonder, is this different enough, or is it similar enough for me to go on? So there's this question, okay? And so to answer that part of when are they similar and when are they different, we employ probability and our understanding of sampling distributions, okay? All right, can I flip to the next slide here? Okay. All right, so let's start off with an example here. Well, here, let me write that out. Okay, so how do we decide when the expectation and reality are, we will say, significantly different enough to say we will reject our initial beliefs. Okay, because that's what we do, right? When the reality and the expectation are different, we say, well, my initial beliefs must have been wrong. Okay, and how do we decide when to make that decision? Okay, so to answer this, we will use probability and sampling distributions. Okay, so let's try out a problem here, or a made-up scenario. Okay. Silly game. All right, you're going to play a game with your friend, or just another person, and the way the game works is you flip a coin, or your opponent flips the coin, and if it lands heads, you win, and if it lands tails, your opponent wins. Okay, it's a very simple game. So you will, play a game with we'll say with an acquaintance. Okay. Okay, flip a coin. Heads, you win. Tails, you lose. Okay, he wins. Okay, and so for whatever reason, the other person is doing all the coin flipping. Okay, so. Okay, all right, so let's say you play 100 games. Okay, so you're going to play 100 games, and we're going to start off with this initial belief, okay? And our initial belief is we're going to assume, even though our opponent is doing all the coin flipping, we're going to assume he's going to play fairly, okay, and not try to cheat. Okay, so we play 100 games. Okay, so we have an initial belief. Okay, opponent plays fairly. Okay. If this belief were true, what would we expect? As far as how many games should we win, what would we expect? We would expect to win 50 out of the 100 games, right? Okay, so if this were true, something around there, right? We expect to win about 50 of 100 games. And because it's random chance, sure, we might win more, we might win less. Okay. All right. Let's say So this is our expectation. Expectation is, you know, our proportion of winning should be okay. All right, let's say the data or the reality. Okay, let's say we win only 45 games. Okay. Opponent did all the flipping. He says, oh man, you only won 45 games. Okay. Do we think our opponent is cheating?
After this course, no.
Or could it have just been bad luck? Okay. So he wins only, we win only 45 games, right? We're expecting to win 50% of the games. We're expecting to win 50 games. We only won 45. Do we call him out and say you're cheating? Huh? Yeah, we say, well, I guess he could have been lucky. I guess I could have been unlucky, right? At this point, we say, you know, 45 versus 50. Is that really different? There's something in our gut that says, maybe it was just bad luck. Okay. So we say, so at this point, or if we're just going with our gut, right? And I'll talk about how our gut lines up with the probabilities and stuff, okay? So at this point, we would not accuse the opponent of cheating.
You wrote we would accuse.
Huh?
You wrote we would accuse.
Oh, we would not accuse, I'm sorry. That's a big difference. That's a key adverb to leave out. We would not accuse the opponent of cheating, okay? We might say, we just got unlucky. Okay? At the same time, does it mean our opponent was playing fairly? Could our opponent have been cheating?
Yes, there is possibility.
There is possibility. There is that possibility. The opponent could have been cheating, but knew not to push it too far to trigger suspicion, right? And left it in the zone where it's just like, you were just unlucky, and left it at this kind of this plausible thing, right? So this is like a tactic of con artists, right? They, you know, when they cheat you, they don't do it so blatantly where it's very obvious that you're being cheated. They
remind me of the movie Focus with Will Smith.
Oh yeah, I've seen that movie. Yeah, Margot Robbie and Will Smith in 2 movies now that were all right. So you know, we might say we were unlucky, okay, and but at the same time, the opponent could be cheating. It's just you know, this isn't enough for us to clearly conclude that he is or is not cheating, okay? Opponent could be cheating. But we do not have enough to say yes or no. Okay. On the other hand, let's have the same situation. Okay. Can I flip? I'm gonna flip to the next slide here. Okay. So we'll say same game. Okay. Play 100 times. Okay. And so again, our expectation is that we win, you know, 0.5 of the games. Okay, and we'll say in the reality, our data says, you know, we won only, we'll say, let me think here. So we'll say we won only 35 of the games. Okay, meaning he won 65 games. Okay. Do you feel like he's cheating now? Okay, this feels a lot more, in our gut we feel like, yeah, I don't think this could have happened just from bad luck, right? Yeah, bad luck might cause me to lose a few more games, but bad luck shouldn't cause me to win only 35 of the games. This is like really, really, really bad luck, right? So our gut now says, you know, this is not the work of bad luck alone, right? Okay, and we now suspect that our opponent has cheated us, okay? Okay, because this time the reality differs quite a bit from the expectation, right? Okay, and so, and this is, you know, we're just kind of going off of gut feelings right now, okay? And so, to kind of, rather than just saying, you know, my gut says this and that, you know, what if you win 39 games? Is that enough to accuse him of cheating? Okay, what about 42? Is that enough? Maybe, maybe not, okay? Rather than just kind of going off of these gut feelings, we're going to use probability to answer these questions, okay? And so the thing that we go for is we're going for something called the p-value, okay? And this is a very important term or concept, okay? And the p-value is the probability of observing our data. Okay, this is kind of the key thing. The probability of observing our data, and then we throw in this phrase, or something more extreme. If the null hypothesis were true. Okay, so in these problems, what did we say our initial belief was?
The initial one, that you did not choose bad luck.
Yeah, the initial belief in our example was, the initial belief or our null hypothesis was that our opponent is playing fairly. Opponent who's doing all the coin flipping is playing fairly. Okay? So we can ask, well, if this belief is true, if our opponent is playing fairly, what is the probability of observing our data? Okay? And that's going to be our p-value. If our opponent plays fairly, of observing our data. That's what we want to know. Okay. All right. So let's answer those questions in the context of this problem here. So, okay, so we'll do, we'll look at scenario 2, which was 100 games, and we won only 35, right? Okay, and so we want to know if we play fairly, okay, if we are playing fairly, what is the probability that, 100 coin flips ends up with only, 35 heads? Okay, and then, and if we were to accuse our opponent of cheating at 35 heads, we would also accuse him of cheating at 34 heads or at 33 heads or anything less, right? So it's not just what's the probability that we end up with only 35 heads, but it's only 35 heads or less. Okay? Can we answer this question? Yes, this is a sampling distribution problem. This is, you've got n is 100, and we're asking what's the probability that p hat ends up being 0.35 or less if p is 0.5, okay? This is a sampling distribution problem. So hang on. This is a sampling distribution problem, and it's basically saying you're taking a random sample of 100 flips, random sample of 100. In the population, you should be getting 0.5 heads, right? The population, the probability in the population is 0.5. Okay, and we're asking what is the probability that p hat ends up being 0.35 or less? Okay, can we answer this? Yes. Okay. So what is the p we're using in this problem? P is 0.5, and our n is 100. Okay, and so we have in a normal model, we're going to go to 0.5, and we want to know what's the probability of being at 0.35 or less, right? So what do we have to do? Get our standard error. And that's going to be what? P times 1 minus P over N. So this is 0.5 times 1 minus 0.5 divided by 100, and we take the square root, and conveniently we get 0.05. We should, if you do your calculation. How did I know that? Well, because I picked these numbers in a way to give me that, but I can also show you right here. Okay. So I do what? 0.5 times 1 minus 0.5 divided by 100 and 0.05. Okay. So that's my standard error. So my z-score is going to be 0.35 minus 0.5 divided by 0.05, right? Divided by our standard error. Okay, and I get a z-score of -3. Okay, if I want to do that, I can also do that right here. 0.35 minus 0.5 divided by 0.05, and I get -3. All right. And so what is the area to the left of -3? It's a very small number. 0.0013. I'll take you at your word. Okay. So we have 0.0013. Okay. And so this is the question. If we are playing fairly, so the truth is if we played 100 games, could bad luck, is it truly possible for bad luck to give me only 35 wins? Yeah. Technically it is possible, okay? How often does that happen? It happens with probability 0.0013. It happens with about 1 in 1,000, okay? So if we played, if we repeated this 1,000 different times, one of those times, bad luck could cause me to win only 35 games out of 100, okay? And so this is what we're faced with, okay? We say, oh, I only won 35 games out of 100. I could choose to believe that it was just really, really bad luck. I happened to be the 1 in 1,000 case where this happened. Or I can say, my initial belief is probably wrong, or my initial belief is wrong, and it's not that we're playing fairly and I just got really unlucky, but rather our opponent is doing something to disadvantage us. Okay? And so what does your gut tell you? It says, well, we probably didn't get this unlucky. Technically, it's possible. It is technically possible that we just got really, really, really unlucky. Okay? With a probability of 0.0013. But because this is so small, we're almost willing to just ignore this possibility. Okay? And we're going to conclude that we're being cheated. Okay? So I'm going to just flip to the next slide. So our p-value is equal to 0.0013. And that means, if we play 100 fair games, it is technically possible to win only 35 games because we had very bad luck. Okay? But the probability of that happening is only 0.0013. Okay, so this probability is so small enough that we are willing to almost ignore the possibility that we had bad luck. Okay, and instead we conclude that our opponent was cheating somehow. So in this case, so we're saying, was the reality and the expectation, were they quite different? And we can answer that question kind of objectively with this p-value. We say, well, what's the probability of getting the data that we have if the null hypothesis were true? And under that, if the null hypothesis were true, it is technically possible to get our data, but our data arrives with only a probability of 0.0013. Is this line of thinking okay? Yes?
Yeah, but the question is probably going to go to next. When you're not sure, when you said like
Yeah, so okay, so let's look at the other scenario, and then we'll look at kind of the in between, and we'll think about the in between cases. Okay. All right. Just want to make sure this part's okay. I'm gonna flip to the next page. All right. So let's look at the scenario 1. Okay. Again, we play 100 games. Okay. We expect to win 50 games. All right, and we won only 45. Okay, and so we say if we were playing games fairly, what's the probability that, okay, could bad luck give me only 45 wins, and what's the probability of that happening? Okay. Could just random chance lead to only 45 wins? Okay, and if so, or I mean the answer is yes. Okay. Okay, what is the probability of getting 45 wins or less from chance alone? Okay, and so in this scenario, we've got basically the same setup. And this time, we have 0.5 in the middle, and we're going to look at the cutoff at 0.45. And we want to know what's the probability of getting 45 or less. So our standard error is actually the same as before. 0.5 times 1 minus 0.5 divided by 100. Inside the square root, we have a standard error of 0.05. Our z-score this time is 0.45 minus 0.5 divided by our standard error. And we get a z-score of -1. Okay, and so when we look that area up in the table,
0.8413.
we should have gotten -1, so we should have 0.1587. Yeah, okay. So we would have z is -1, and we get this area is 0.1587. Okay. And so this basically means, this is about 16% chance, okay? Almost 1 in 6. If you play 100 games, about 1 in 6, okay, about 16% of the time, bad luck is going to lead you to just winning only 45 or fewer games. Okay, so if we play 100 games fairly, okay, random chance can cause us to win only 45 games or less, okay, with a probability of around 16%. Okay? And so, it's not a huge probability, but it's certainly not a negligible probability. It's not a probability that we're going to just completely ignore. Okay? And because of that, we're going to say, okay, well, maybe I did get unlucky. Okay? It doesn't mean that the person wasn't cheating, but it's possible that we just got unlucky. Okay? So this time our p-value is 0.1587. Okay, this is not a negligible percentage, or proportion. Okay. So we are not ready. So we are not going to say that our opponent is cheating. Okay. Okay. It also does not clear. It also does not mean he isn't cheating. Okay. But it does, but we do not have evidence that he is cheating. Okay. So essentially here is that we are, we do not reject our initial belief. So we do not reject the null hypothesis. Okay, and so as far as conclusions go, as far as deciding whether the reality and the expectation match up closely, or whether, whether we should reject the null or not reject the null, we draw an arbitrary line, okay? We pick an arbitrary value, and that value is called alpha. Okay, so to make our decisions, alpha. Okay, this is called the significance level. Okay, and just kind of over time, the accepted, most commonly used value for alpha is 0.05. Okay, but that's just kind of an arbitrary value. But that's kind of become the value of choice. Okay, so the most common and default value of alpha is 5%. So basically, if the p-value ends up being bigger than alpha, or in most cases, if the p-value is bigger than 5%, we are not going to reject the null hypothesis. And on the other hand, if the p-value ends up smaller than 5%, we will reject the null hypothesis. Okay. So we do not reject the null hypothesis, meaning, the reality and expectation were not significantly different. And then if the p-value is smaller than alpha, we do reject the null hypothesis. Oh, I'm sorry. H0 is abbreviation for the null hypothesis. Okay. If H0 is a abbreviation for the null hypothesis, and that means, the reality and the expectation are significantly different. Okay. And so, you know, if alpha is 0.05, then that means if your p-value ends up being like 0.06, then you don't reject and you say it's not significantly different. Okay? And on the other hand, if your p-value ends up being 4%, or even like 4.9%, 0.049, where it's less than 0.05, you say, yes, it is significantly different. And then there might be a question, well, what's really the difference between p-value 0.049 and p-value 0.06 and these questions? And these are good concerns and things to have, but that's just kind of the side effect of drawing an arbitrary line. Yeah. Yes, question?
Who created that line? Who decided that 5% is the line of like saying that's it?
I don't know. Well, okay, so no, actually, there's kind of Ron Fisher and Gossett. These are kind of historical statisticians, and just kind of over time, this has become the accepted value. Okay. And that's just, so these have come under a little bit of fire, like 5%, that seems like an arbitrary value. Why are we depending on that? And, you know, there are some concerns about that. And I think those are valid concerns because you do see a lot of research papers being published with p-values that barely made the cut, like p-values of 0.047, 0.048. You see a lot of these types of things. And, you know, is that good or bad? It certainly is a little something to think about. But, you know, we accept arbitrary lines drawn in life, and we don't even question it. Like, in the US, you can get your driver's license at age 16, right? Is there a difference between the motor and cognitive capability between someone who's, you know, 1 week away from turning 16 and someone who's 16? Probably not, but by law we say at 16 we can trust you with this, you know, several thousand-pound hunk of metal traveling at 65 miles per hour, and that's okay, you know? You know, at age 18, we say, okay, you're able to join the military and shoot guns and whatever, and that's fine. But if you're 17 years old and 11 months, you are not trustworthy enough to make these decisions. There are arbitrary lines, but we've accepted that, right? And that's what happens. Yes?
Remind me what CLT stands for?
Central limit theorem. CLT is central limit theorem.
Okay. And who decided it has to be at least 10 successes and 10 failures? The same people?
Yeah, it's kind of the 10 successes and 10 failures. There's kind of, again, a little bit arbitrary saying, like, at this point, the sampling distribution and the normal distribution look, quote, similar enough. Other textbooks might say like 8, you know, others will say a little bit higher. 10 has become kind of the accepted number, probably because we have 10 fingers and so much of our life is shaped by the fact that we have 10 fingers. You know, and sometimes you have these unintended consequences of arbitrary lines, but that's in order to have systems that are easy to teach and easy to understand. Arbitrary lines kind of work the best, right? It's a lot harder to say, well, you have to look at the data and the context of the situation and then make nuanced decisions about whether the p-value you get of, you know, 4.8%, is that significant or not? Perhaps in the context of a certain situation, it's not, okay? But that's a lot harder to teach and a lot harder to understand, and this idea of fairness. So we just say, wow, 5%, this is the line. Okay. All right, so let me kind of just formally define, not define, but just set up some steps in the process of hypothesis testing, and then we'll take a look at that. Okay, so we'll do hypothesis testing in 4 steps. Okay, this is going to be, I don't know, a few pages of notes, but these are, I don't know, very key. And if you understand these 4 steps of hypothesis testing, because we're going to encounter hypothesis testing a lot, and a lot of your final exam will depend on hypothesis testing and confidence intervals and things like that. So, you know, make sure you get these 4 steps for hypothesis testing, okay? And so specifically here, I'm going to outline hypothesis testing for P based on one sample of data, okay? The fact that we have P for proportions, what kind of data are we dealing with? Categorical variables, okay? Okay, so step 1 is create your hypotheses. Okay, and so you have a null hypothesis, which we write as H0. Okay, and the null hypothesis is P is equal to some number P0. Okay, and so for example, we would say the null hypothesis is that P is equal, I don't know, to 0.42. Okay, and so in this case, P0 is 0.42. So P0 is some number. And then we have the alternative hypothesis. Okay, so the alternative hypothesis is written HA. And then it's identical to the null hypothesis, except we replace the equal sign with either a not equal or a greater than or a less than sign. Okay, so in this example, it would be, the alternative would be P is not equal to 0.42. Okay, so all right, the alternative hypothesis is identical to the null, except the equal sign is replaced with either a not equal sign, a greater than sign, or a less than sign. Okay? If the alternative hypothesis has a not equal sign, this is called a two-tailed test. And if the alternative has a less than sign or greater than sign, it is called a one-tailed test. Okay, and note that the null hypothesis will always have an equal sign. Okay, and so when you're doing hypothesis testing for P based on one sample, your null hypothesis is always going to be P is equal to some number. Okay, and this number that appears here, this is called P0. So in this case, our P0 is 0.42. Okay, and that's creating your hypotheses. Your choice of whether to use greater than, less than, or not equal depends on how the question is written. Okay, and I'll give you an example showing how to figure out what to use.
Regarding the last part, when it says that it's going to always have an equal sign.
Yes. Meaning it's going to be P is equal to some number. It'll never say, the null hypothesis will never say P is greater than a number or P is less than some number. The null hypothesis will always say P is equal to some number. Okay.
But you said that equal is replaced with not equal or greater or...
For the alternative hypothesis. The alternative hypothesis is identical to the null, except the equal sign has been replaced with something else. Okay?
This is something else.
Yeah. All right, and then your choice of not equal, greater than, or less than in the alternative in HA depends on the question. Okay, examples to follow. Okay, I'm going to flip. All right, so if so we'll say if the question says something like does the data provide evidence that P is different from 0.42? The word different implies, the alternative will be not equal to. Okay, so different means the alternative will have not equal sign. Okay, words like changed, is not the same, stuff like that. All right. If the question says, okay, do we have evidence that P is higher than 0.42? Okay, so in our case we'll have, I'm sorry, alternative. Then over here, higher, larger, more, etc. Then means the alternative will have a greater than sign. So here we're going to have the alternative is P is greater than 0.42. Okay, similarly, smaller, less, lower, etc. The alternative will have a less than sign. Okay. So depending, we'll do an example later, and we'll be able to decide what our null and alternative hypotheses should be. Okay? So step 1, figuring out your hypotheses. Okay? Step 2 is this is kind of the preparation. So technically we're supposed to check conditions to use the central limit theorem. And you know these already: independent and random, large sample, big population, okay, those are your conditions to check. As far as exams go, I'm going to do the checking conditions as a separate section, kind of like what you saw in the quiz today, because it's hard to write a series of questions where the answer is, oh, you were supposed to check the conditions, so you're not supposed to do these calculations or something like that. It feels kind of like I'm setting up for a trap or something. So, so in this case, it'll be kind of separated out. And then the other part is select or identify alpha, your significance level. Okay, and it, you know, if no alpha is specified in the problem, assume alpha is equal to 0.05 as our significance level. Okay. And then step 3 is our calculations. Calculations to get your p-value. Okay, and this can be broken into 3 subparts. So 3a will be get your standard error. So our standard error in this case is going to be the square root of p0 times 1 minus p0 divided by n. What's p0 again? It's the proportion that appears in our null hypothesis, okay? So I'm just going to write the proportion in the null hypothesis. Okay, once you have your standard error, then you're going to get your test statistic. The test statistic is the difference between the reality and the expectation divided by the standard error. Okay? Or we might say observed minus expected. No, let me write that out. Observed minus expected divided by the standard error, okay? Or so put simply, we're going to get a z-score. What we observe in our data is p hat. What we expect, if the null hypothesis were true, is we would expect p0, and we're going to divide that by the standard error. That's our test statistic. And then once you have your test statistic, you're going to look up z in the z-table, okay, to get your p-value. All right, and then so I'm going to have to go to the next slide for this. So whether you want the area to the left or the area to the right or whatever, that depends on the alternative hypothesis, okay? So looking up z in the z table to get your p-value. Okay, so continuing, so that means look at the alternative hypothesis. Okay, look at HA. So if the alternative has a less than sign, okay, your p-value is equal to the area to the left of z. Okay, which means you just look up the z in the table, and what the table gives you is your p-value. Okay, what the table says is the p-value. Okay, if the alternative has a greater than sign, then the p-value is equal to the area to the right of z. Okay, so what do? You do p-value is 1 minus the value in the table.
Can you just change the z-score from plus to negative?
Yes, that's also a perfectly valid way to do it. Okay, and if the alternative has a not equal sign, then we have a two-tailed test. So our p-value is equal to 2 times the tail area. All right, so what is the tail area? The tail area is the area to the left of a negative z value and the tail area is the area to the right of a positive z value. Okay, so if your alternative has a not equal sign, you're going to have to figure out your tail area. It's area to the left of z is negative, area to the right of z is positive, and then you're going to multiply that by 2. That's going to be your tail area. Okay, and that's that's going to be you get your p-value this way. And then once you have your p-value, then you make your conclusion. Okay, and that's step 4. Yes, just go back, sure. Yes?
So you multiply the two z values together, the negative and the positive.
No. You look up the z, okay? Whether it's positive or negative, you're going to either take the area to the left or the area to the right. Once you get that, that's your tail area, and then you multiply it by 2 to get your p-value. Okay, is that good?
Yes, thank you.
All right, so step 4 is going to be make your conclusion. All right, and so if the p-value is greater than alpha, that means you do not reject the null hypothesis, okay? More details would be our data, or the reality, is not significantly different from the expectation. Is not. I keep leaving out these important words. Is not significantly different from the expectation. Or another way is that even if the null hypothesis were true, there is a non-negligible probability of producing our data from random chance alone. Okay. It is important that we say we do not reject the null. Don't say we accept the null, okay? Okay. Not rejecting is not the same thing as accepting, okay? Or, you know, not denouncing is not the same thing as endorsing something. So we cannot say, you know, we're going to say we didn't reject it, but that doesn't mean we accept it. Okay. All right, and then on the other hand, if the p-value is less than alpha, we reject the null hypothesis. Okay, and we say our data is significantly different from our expectation. And we'd say if the null hypothesis were true, if our initial belief were true, it is very improbable for us to observe our data from random chance. Okay, so the fact that we did observe our data causes us to doubt our initial beliefs. Okay, why don't we take a short break here. We'll say 10 minutes, and then we'll resume and we'll do an example and then cover another scenario here.